Before there were myths, before there were kings, before there were even written words, there were objects, silent things, cold to the touch, patient beyond time. Objects that do not speak, yet somehow accuse. They accuse us of certainty, of comfort, of believing we already know how the story begins. Scattered across museums, storerooms, and excavation reports are artifacts that should not exist, not according to the story we tell ourselves about the past. They are not magical. They are not divine. They do not glow or hum or defy gravity. Their provocation is far more unsettling than that, and they are precise. So precise, in fact, that when modern engineers first measured them, the numbers refused to behave. Not because the data was wrong, but because the assumptions behind it were. We are used to thinking of ancient craftsmanship in romantic terms: skilled hands, endless labor, patience stretched across generations. We imagine imperfections smoothed by repetition, error hidden beneath ornament. And often that image is correct, but not always. Because precision is not a feeling, it is a number. It is the difference between a flat surface and one that merely appears flat. It is the distance between the symmetry perceived by the eye and the symmetry confirmed by measurement. It is tolerance, the allowable deviation from an ideal form, expressed not in poetry, but in microns. And when those tolerances shrink beyond what known tools should allow, history begins to tremble. In engineering, precision is unforgiving. A surface flat to within 1/10 of a millimeter is impressive. Flat to within 100th is extraordinary. Flat to within a few microns belongs to a world of controlled environments, vibration isolation, diamond tooling, and machine feedback loops. It belongs to factories, not temples, to laboratories, not burial grounds. Yet in the archaeological record, such numbers are quietly appearing. Not everywhere, not often, but often enough to disturb. These are not objects admired for their beauty alone. They are objects that behave like solutions to problems. Problems that require forethought, repeatability, and an understanding of material behavior under stress. Problems that assume geometry not as decoration, but as a discipline. This is where the mystery begins, not with legends, but with calipers. When researchers affiliated with journals like the Journal of Archaeological Science began applying modern metrological tools to ancient artifacts, the intent was simple: document wear, identify tool marks, and understand manufacturing sequences. No one was looking for miracles. They were looking for data. What they found instead was consistency. Internal symmetries where external symmetry was irrelevant. Axial alignment is preserved through hollow forms, surface finishes that changed abruptly, as though a process had begun, stabilized and ended, rather than faded through fatigue. These are not traits of improvisation. They are traits of control. And control is expensive. It demands energy, planning, and feedback. It demands that the error be visible, measurable, and correctable. In modern engineering, this is achieved through machines. Not because humans lack skill, but because humans lack infinite steadiness, which brings us to the first fracture in the story. If ancient artisans worked only with copper chisels, stone hammers, and abrasive sands, tools well documented in the archaeological record, then certain outcomes should be statistically unavoidable. Asymmetry should accumulate. Internal surfaces should drift. Tool chatter should betray fatigue. Error should compound, not cancel. And yet, in some cases, error appears disciplined, not eliminated, but constrained. At sites in Egypt, Greece, the Andes, and the Indian subcontinent, isolated objects emerge that do not resemble the technological baseline of their surroundings. They are not better versions of the same thing. They are different things entirely. Consider briefly 3 signposts, not destinations, not explanations, simply markers on the road. In Egypt, deep beneath Saqqara and Giza, stone vessels carved from granite, one of the hardest naturally occurring stones, display internal profiles of startling regularity. not decorative, not symbolic, but mathematically consistent. In the Mediterranean, pulled from a shipwreck and corroded by centuries of salt water, a bronze mechanism composed of interlocking gears encodes astronomical cycles with mechanical fidelity, rivaling clockwork built nearly 2,000 years later. And high in the Andes, vast stones weighing tens of tons interlock with neighboring blocks so tightly that even a blade cannot pass between them, not through mortar, but through geometry. None of these objects on their own rewrite history, but they share a troubling trait. They obey rules, rules of alignment, rules of repeatability, rules of precision that suggest intentionality beyond aesthetics. They behave less like art and more like answers. This is where the question sharpens. Were ancient humans more technologically capable than we believe, capable not merely of ingenuity but of systematic precision? Or are we, modern observers, misunderstanding what precision itself requires? Have we mistaken machinery for necessity rather than convenience? Because precision does not demand electricity. It does not require silicon. What it requires is feedback, a way to compare what is against what should be. And feedback can exist in many forms: tactile, visual, acoustic, iterative. Nature herself achieves extraordinary precision without gears or wires. Crystals form with atomic regularity. Orbits settle into stable resonances. Structures self-correct through constraint rather than force. So perhaps the question is not whether ancient people had machines like ours, but whether they understood principles we now outsource to machines. This is why the debate has intensified in recent years, not in fringe circles, but within peer-reviewed literature. Publications in Nature Archaeology increasingly emphasize measurement over narrative, restraint over speculation. The focus has shifted from what ancient people believed to what ancient objects demonstrate, and demonstrations are difficult to argue with. Still, caution matters. Extraordinary claims demand extraordinary evidence, and precision alone is not proof of lost civilizations or forgotten technologies. Skilled labor, applied over time, can achieve astonishing results. Experimental archaeologists have shown that repetition can refine technique. That error can be trained away. Those hands, guided by templates and discipline, can rival machines under the right conditions. But not all conditions, and not all numbers. This is the uncomfortable middle ground, where neither dismissal nor fantasy holds, where skeptics and iconoclasts are forced to share the same measurements, even if they disagree on their meaning.
It is here that the story truly begins.
Not as a rebellion against mainstream archaeology, but as a question posed to it. If even one artifact, just one, demonstrates a level of precision that cannot be reasonably explained by known methods, then history does not collapse, but it must bend. And bending history is dangerous, because it forces us to ask whether progress is linear, whether knowledge always accumulates, whether complexity once achieved must inevitably advance rather than vanish. If you are finding this journey unsettling, if the questions feel heavier than the answers, then you may wish to stay with us. Subscribing is not a commitment to belief, only to curiosity. And curiosity, as history reminds us, is often the beginning of disruption. Because in the next step of this journey, we will stop speculating entirely. We will measure. We will bring lasers, scanners, and modern instruments into direct conversation with ancient stone and see what survives that encounter. And if the numbers continue to resist us, then the anomaly will no longer belong to the past. It will belong to us. Because if even one artifact violates our assumptions, truly violates them, then the question is no longer what ancient humans were capable of. The question becomes, how many other assumptions are resting on foundations just as fragile? Speculation has a sound. It is the murmur of possibilities, the low hum of ideas brushing against one another in the dark. Measurement, by contrast, is silent. It does not persuade, it does not accuse, it simply records. And in doing so, it crosses a line that stories cannot. To measure an object is to suspend belief, not only belief in legends, but belief in comfort. Because once a number is written down, it no longer belongs to interpretation alone. It can be checked, repeated, challenged. It either holds or it collapses. This is the threshold where the mystery changes character. For centuries, ancient artifacts were judged by eye, described in words like smooth, symmetrical, finely worked, admirable but vague. The human eye is forgiving. It smooths error. It forgives deviation. It confuses repetition with precision. What looks perfect is often merely familiar. Engineering does not allow that luxury. In engineering, precision begins with a question. How close is this object to an ideal geometry? Not aesthetically, mathematically. How flat is a surface? How circular is a curve? How coaxial is a hollow form? And crucially, how consistent are those properties across the whole object? These are not philosophical questions. They are answered with instruments. Modern metrology, the science of measurement, was not developed to study the past. It was developed to build engines that do not tear themselves apart, aircraft that do not shake apart at altitude, and machines whose tolerances must remain stable under heat, vibration, and load. It is a discipline obsessed with error, not eliminating it but understanding how it behaves. When archaeologists began borrowing these tools, they did so cautiously, not to provoke controversy, but to reduce it. Measurement was meant to settle arguments, not ignite them. The first of these tools is laser scanning. A laser scanner does not see an object, it interrogates it. Millions of points are projected onto a surface, each reflecting back with precise spatial coordinates. What emerges is not an image, but a cloud, a dense mathematical reconstruction of form, stripped of texture, stripped of narrative. It reveals things the eye cannot. Minute warping, asymmetries hidden by polish, deviations so small they vanish under casual inspection. A laser does not care if an object is sacred, ancient, or beautiful. It cares only about distance. Then there is white light interferometry. This technique is less intuitive and more unsettling. White light is split and recombined, producing interference patterns that reveal surface variations down to fractions of a micron. It can detect undulations thinner than a human hair by orders of magnitude. It is used to inspect semiconductor wafers, optical lenses, and precision bearings. Applied to ancient artifacts, it does something quietly radical. It asks whether surfaces thought to be smooth are actually controlled. Not polished, controlled. A polished surface can still wander. A controlled surface holds its geometry across space. Finally, there are coordinate measuring machines, CMMS. These are the giants of precision measurement. Mechanical arms or probes that physically trace an object's geometry, recording spatial coordinates with extreme accuracy. They are the arbiters of manufacturing quality in aerospace and automotive engineering. If a component fails a CMM inspection, it does not fly, it does not drive, it does not exist. When CMMs touch ancient stone, they bring with them an unforgiving standard. They assume nothing about how an object was made. They ask only whether it conforms to itself. What emerges from these measurements is not a story, it is a data set. And data sets have a way of outliving arguments. Between 2023 and 2024, a series of studies published in the Journal of Archaeological Science began applying these techniques systematically. Not selectively, not sensationally. The goal was not to prove impossibility, but to document variability. One of the figures associated with this shift is materials engineer Dr. Amelia Sparavigne. Her work does not chase lost civilizations or forgotten technologies. It does something far more disruptive. It measures. Using high-resolution laser scanning, her methodology reconstructs the internal and external geometry of ancient stone artifacts at a resolution that eliminates subjective interpretation. The scans are then analyzed for symmetry, concentricity, surface deviation, and repeatability. No conclusions are embedded in the process. The scanner does not know what era it is examining. The software does not care what tools historians expect to find. The mathematics treats every object equally. This is the crucial point, and one that is often misunderstood. Measurement does not interpret intent. It does not tell us why an object was made, or how it was valued, or what it meant to those who created it. It does not imply aliens or lost empires or secret knowledge. It reports only what is present. A surface is either flat within a given tolerance, or it is not. A cavity is either concentric, or it drifts. A curve either maintains radius, or it degrades. These are binary outcomes. In modern mechanical engineering, tolerance analysis is used to determine whether a part can function as intended. The tighter the tolerance, the more controlled the manufacturing process must be. MIT's mechanical engineering literature is explicit on this point. As tolerances shrink, error sources multiply. Thermal expansion, vibration, tool wear, and human inconsistency all become dominant factors. Which is why machines are used, not because humans are incapable, but because humans are variable. This is what makes the application of these tools to ancient artifacts so unsettling. Not because the measurements are shocking in isolation, but because they introduce a comparison that history has avoided. They place ancient objects on the same analytical footing as modern components, and sometimes they do not embarrass themselves. It is important to be precise here, because exaggeration is the enemy of understanding. Most ancient objects do not exhibit extreme precision. Most stonework shows clear signs of manual shaping, abrasion, drift, and correction. The archaeological record overwhelmingly supports human craftsmanship operating within known constraints. But anomalies are not dismissed by majority rule. Engineering does not work that way. One failed component can bring down an entire system. One unexpected tolerance can invalidate an assumption. The role of metrology is not to rewrite history, but to identify where history's models strain under scrutiny. And this is the point of no return. Once an object has been scanned, probed, and reconstructed mathematically, it cannot be unmeasured. The data exists. It can be revisited, reanalyzed, challenged by anyone with access to the methods. The mystery no longer belongs to belief. It belongs to numbers. If you find yourself drawn into this shift, from narrative to measurement, from romance to reality, you may wish to remain with us. Subscribing is not an act of agreement, but of patience, because what follows demands both. In the next step of this journey, we will examine the results of these measurements, not broadly, not vaguely, but object by object. We will begin with a class of artifacts so precise internally that even modern engineers paused before trusting their own instruments. And then we will ask a question that metrology cannot answer, but cannot avoid provoking. What happens when modern machines examine objects made before machines were supposed to exist? If this question intrigues you, make sure to subscribe to our channel. We would love to take you through different journeys to the heart of the universe. The desert around Saqqara is not subtle, its heat is blunt. Its light exposes everything it touches. And yet, buried beneath this abrasive landscape, objects were found that seem almost offended by disorder. They are small, easily overlooked, stone vessels, bowls, jars, containers, many no larger than a human forearm. At first glance they appear unremarkable, even austere. No hieroglyphs, no decoration, no narrative scenes, just stone shaped into form. But when engineers stopped looking at them as art and began treating them as components, something quietly astonishing emerged. These vessels date to Egypt's pre-dynastic period, more than 5,000 years ago. Long before pyramids, long before dynasties, long before the state machinery we associate with monumental construction. According to conventional timelines, this was an era of simple tools, copper chisels, stone pounders, abrasive sands. Effective, yes, but limited. And yet these vessels were carved from granite. Granite is not a cooperative material. On the Mohs scale of mineral hardness, it averages between 6 and 7, far harder than copper, which sits at roughly 3. Granite's strength comes largely from quartz, a crystalline mineral whose hardness alone reaches 7 on the Mohs scale. Quartz does not yield easily. It fractures, it resists, it punishes inconsistency. Modern machinists do not cut granite casually. They grind it, polish it, shape it slowly, with diamond abrasives and controlled feeds. They understand that granite does not forgive uneven pressure. Any lapse leaves scars. This makes the internal geometry of the Saqqara vases so disturbing, because the most precise features of these objects are not on the outside, where hands can adjust and eyes can guide, but on the inside. Hollow interiors carved deep into solid granite, exhibiting concentricity and symmetry that remain stable across their depth. This is where measurement becomes unavoidable. High-resolution laser scans performed and analyzed by researchers, including Dr. Emilia Sparavigna, reveal internal axial symmetry deviations measured in mere microns. In several documented cases, the variance from ideal rotational symmetry falls within approximately 0.005 millimeters, around 0.0002 inches. To put that number in context, this level of tolerance is comparable to components used in modern fluid systems, bearings, and optical mounts. It is far tighter than what is typically achievable through freehand abrasion, especially inside enclosed cavities, and it is not a single measurement. It is repeatable across multiple vessels. These interiors are not merely smooth, they are consistent. The radius of curvature remains stable. The walls do not wander. The central axis holds. In mechanical engineering terms, this implies controlled material removal around a fixed reference. Either the stone was rotated relative to the tool, or the tool was rotated relative to the stone, and that rotation was maintained with discipline. Copper tools and sand abrasives can remove granite. This is not in dispute. Experimental archaeology has demonstrated this repeatedly. But removal is not the same as control. Copper deforms under load, sand grains fracture unpredictably, manual pressure varies with fatigue. Over time, these variables accumulate errors. The deeper the cavity, the harder it becomes to maintain symmetry, because the tool loses reference. Modern engineers are keenly aware of this problem. Internal machining is always more difficult than external shaping. Visibility decreases, access narrows, error multiplies. To achieve the kind of internal regularity seen in these vessels using copper tools would require not just extraordinary skill, but a method to detect and correct deviation continuously. Which raises a question no one intended to ask. What feedback mechanism was in use? Some researchers have proposed that simple rotational devices, primitive lathes, could account for the symmetry. This is plausible in principle. Rotational shaping naturally enforces symmetry, even with relatively simple tools. But granite resists continuous cutting. It prefers intermittent abrasion. Maintaining a stable axis while grinding internally without rigid bearings or hardened tools becomes exponentially harder. Others have suggested that the vessels were shaped externally, then hollowed through prolonged abrasion. But this does not explain the precision of the internal profiles, especially where the internal geometry does not mirror the external form. In several cases, the interior is more regular than the exterior, a reversal of expectation. This inversion matters. It suggests that the priority was not appearance but geometry. It is at this point that a more controversial idea enters the discussion, cautiously, reluctantly, not as a conclusion, but as a question. Ultrasonic machining. In modern industry, ultrasonic machining uses high-frequency vibrations to drive abrasive particles against hard materials. The process allows brittle substances like granite and glass to be shaped with remarkable precision, minimal tool wear, and excellent surface control. The tool itself does not rotate aggressively. Instead, it vibrates, tens of thousands of times per second, allowing abrasives to erode material evenly. No one claims that pre-dynastic Egyptians possessed ultrasonic generators or piezoelectric transducers. That would be absurd. but the principle is unsettling. Vibration-assisted material removal reduces cutting force. It minimizes chatter. It stabilizes abrasion. In modern settings, it allows internal cavities to be shaped with tolerances otherwise unattainable through static grinding.
The reason this hypothesis persists is not that it explains everything, but because it explains something very specific: why tool signatures are missing.
In conventional machining, tools leave marks, striations, directional scratches, chatter patterns. These signatures betray motion, pressure, and fatigue. They are fingerprints. Yet many Saqqara vessels show interior surfaces that are remarkably uniform, not mirror-polished but consistent. Where marks exist, they do not always align with expected manual motions, and where they should accumulate deep inside, they sometimes fade. This absence is not proof of advanced technology, but it is evidence of a gap. British Museum artifact records confirm the dating, provenance, and material composition of these vessels. They are not misattributed. They are not modern intrusions. Their context is secure, which leaves us with a narrow, uncomfortable space between what is known and what is assumed. No one is arguing that ancient Egyptians violated physics. Granite behaves the same now as it did then. Quartz vibrates, abrasives abrade, geometry obeys the same laws. The question is simpler and more dangerous. Did ancient artisans possess process knowledge that we no longer recognize as such? Not machines, perhaps, but methods. Not electricity, but control. In engineering, precision is not always a product of technology. Sometimes it is a product of obsession, of iteration, of systems refined until error becomes predictable and therefore correctable.
But even obsession leaves traces.
Which brings us to the quietest and most troubling aspect of the Saqqara vessels. Precision this high usually leaves signatures, tool paths, wear patterns, transitional errors. So where are they? Because if the tools are absent from the stone, then the next step of this journey is unavoidable. We must stop asking what these objects are and begin asking how they were made, when the evidence refuses to speak the language we expect. When an object is made, it remembers how it was made. This is not philosophy, it is physics. Every tool, no matter how simple, leaves a trace. Every interaction between material and force produces a signature, a microscopic record of motion, pressure, rhythm, and failure. Engineers rely on these signatures every day. They are how faults are diagnosed, processes refined, and mistakes reconstructed long after the machine has stopped moving. Stone is an especially honest witness. Unlike wood or metal, stone does not heal. It does not bend and return. It fractures, abrades, and retains memory. The surface of a worked stone is a frozen event, the last conversation between tool and material. Which is why the problem of tool marks has become one of the most uncomfortable fault lines in modern archaeology. To understand why, we must first be clear about expectations. When stone is worked using hand tools, chisels, pounders, picks, it exhibits characteristic features. Chisel chatter produces repeated rhythmic indentations, often uneven in depth as the hand tires or angle shifts. Abrasion with sand leaves linear striations, aligned with the direction of motion, widening and narrowing as pressure fluctuates. Rotary grinding, when done manually, introduces asymmetry, slight ovality, drift from axis, and cumulative error over depth. These patterns are not subtle, they are predictable. Experimental archaeology has catalogued them extensively. Researchers such as Dennis Stocks, whose decades of work reconstructing Egyptian stoneworking techniques remain foundational, demonstrated that copper chisels combined with quartz sand can shape granite. Stock's experiments, published and replicated, show abrasion grooves, tool chatter, and progressive irregularity, exactly what engineers would expect. And this is where the refusal begins. Because when these expected signatures are sought on certain ancient artifacts, they are incomplete or absent. Not everywhere, not universally, but selectively. And that selectivity is the problem. In the Saqqara granite vessels, interior surfaces often show a uniformity that resists easy classification. Abrasion striations, when present, do not always align with known manual motions. Chisel chatter is minimal or missing in regions where force concentration should have been unavoidable. Rotary asymmetry, the slow drift off axis that plagues manual rotation, is constrained to levels that challenge freehand explanation. This does not mean the surfaces are pristine. They are not mirror smooth, but they are controlled. This distinction matters. A surface shaped by brute force looks chaotic at small scales, even if it appears smooth from a distance. A surface shaped by a stable process looks orderly even when unfinished. The question is not whether ancient tools could work granite. The question is why the stone does not consistently show how they did. British Museum replication studies conducted in the late 20th and early 21st centuries attempted to reproduce granite vessels using period-appropriate tools. These experiments succeeded in producing vessels of roughly similar shape, an important achievement, but the resulting interiors showed unmistakable signs of manual abrasion, uneven wall thickness, elliptical deviation, and striation density that increased with depth. In other words, they behaved exactly as expected, which raises a dangerous comparison, because some original artifacts do not behave this way.
This discrepancy has produced two broad camps, neither fringe, neither conspiratorial.
On one side are experimental archaeologists, many of whom argue that we are underestimating the power of iteration. That ancient craftsman, working within guild systems and transmitting skill across generations, could refine technique to levels rarely attempted today. They emphasize time as a tool, years, even decades, spent perfecting a single class of object. Dr. Dietrich Klemm and Dr. Rosemary Klemm, noted Egyptologists and geologists, have long argued that material sourcing and tool use in ancient Egypt were more sophisticated than often portrayed, not technologically advanced in a modern sense, but methodologically refined. They point out that stoneworkers may have used templates, guides, and sequential abrasion strategies now lost to time, that what appears anomalous may simply reflect a depth of practice modern replicators lack.
This is a strong argument, and it cannot be dismissed lightly.
But it has limits. Iteration improves consistency, not invisibility. No amount of practice removes the fundamental physics of tool-material interaction. Copper deforms, sand fractures, hands tremble. These facts do not vanish with skill. They are mitigated, but they still leave traces. This is where skeptical voices from within archaeology become unexpectedly divided. Egyptologist Dr. Zahi Hawass has consistently rejected claims of unknown technology, emphasizing workforce organization, patience, and scale. In his view, extraordinary precision is an illusion born of selective measurement and modern obsession with numbers. Ancient craftsmen, he argues, achieved what they needed, no more, no less. Yet even Hawass acknowledges that some objects exhibit craftsmanship of remarkable quality, without fully addressing the internal geometry problem. Meanwhile, materials scientists examining the same artifacts ask a different question, one less concerned with narrative and more with process. If a surface shows fewer tool signatures than expected, what does that imply about force application? Low-force processes behave differently. They reduce chatter. They distribute abrasion. They blur individual tool marks into continuous textures. In modern contexts, such effects are achieved through vibration, rotation with rigid constraint, or compliant tooling systems. Again, no one is claiming ancient Egyptians possessed factories. But processes do not require factories to exist. A bow drill introduces rotation. A weighted spindle introduces inertia. A suspended tool introduces compliance. Sound introduces vibration. Each of these modifies how force enters material, and therefore what signatures remain.
This is where the problem becomes philosophical.
Archaeology is accustomed to identifying tools. It is less comfortable identifying processes. Tools decay, wood rots, copper is recycled, stone vessels endure. If the process relied more on system behavior than on discrete implements, the archaeological record would preserve the result, but not the method. This is not a comfortable idea. It resists cataloging, it refuses reconstruction through simple replication, and it explains why debates around tool marks grow heated. Because to accept that the stone does not fully reveal its maker is to accept uncertainty, not about who built these objects, but about how knowledge itself is lost. The refusal of the known world occurs here, not because history is wrong, but because it may be incomplete. If brute force, repetition, and known tools cannot fully account for the absence of expected signatures in certain artifacts, then something else must have mediated the interaction between human intent and stone response. Not magic, not aliens, but a process that behaves differently enough to leave a quieter trace. And that silence, that absence of chatter, of drift, of error, is what draws us deeper into the mystery. Because stone does not lie. If not brute force, then what process shaped the stone? There is a moment in every investigation when force gives way to motion, when the question is no longer how hard something was struck, but how steadily it moved. Rotation is one of the oldest solutions to precision ever discovered. Long before engines, long before electricity, long before mathematics was written down, rotation offered a simple miracle: symmetry without constant correction. Once an object turns around a stable axis, error no longer accumulates randomly. It is averaged out. Deviations cancel themselves. The circle enforces discipline where the hand cannot. This is not philosophy. It is mechanics. A rotating system does not need intelligence, it needs consistency. Which is why rotation appears so early in human history, in pottery wheels, bow drills, spindle whirls. Wherever humans encountered the limits of manual shaping, rotation quietly stepped in as a solution. It did not eliminate effort, it transformed it. And in stone, that transformation leaves unmistakable signs: spiral grooves, uniform curvature, radial consistency that does not care about the strength or fatigue of the operator. These are the fingerprints of rotational processes, not of brute force, but of controlled motion. This brings us to the Ajanta caves of India. Carved into basalt cliffs between the 2nd century BCE and the 6th century CE, the Ajanta complex is celebrated for its murals, sculptures, and architectural ambition, but hidden among the devotional grandeur are features that receive far less attention: stone pillars whose geometry refuses to behave like hand-carved objects. These pillars are not merely cylindrical, they are true cylinders. Their curvature is uniform along their length. Their diameter remains consistent. And most tellingly, many display faint spiral striations, shallow, continuous grooves that wrap around the shaft in a helical pattern. This is not decoration. In materials science, spiral striations are diagnostic. They indicate relative motion between tool and workpiece under rotation. The pitch of the spiral reflects feed rate, how fast the tool advanced along the axis as rotation occurred. The uniformity of the pitch suggests stability. No stops, no resets, no wandering hand. The Archaeological Survey of India has documented these features extensively, noting their regularity and recurrence across multiple caves. While official interpretations often describe them as the result of advanced craftsmanship, the geometry itself demands a more specific explanation. Freehand carving does not produce helices. Hands jitter, pressure varies, direction shifts. The result is irregular scoring, short overlapping marks that betray interruption. A helix, by contrast, is continuous. It implies sustained motion around a fixed axis. This does not require electricity. That point must be made explicitly, because misunderstanding thrives in silence. Rotation predates electricity by millennia. A bow drill rotates, a potter's wheel rotates, a weighted spindle rotates. Gravity, inertia, and tension are sufficient. What matters is not power source but constraint. Once rotation is constrained, once wobble is suppressed, material begins to behave differently. Modern material science is clear on this. Rotational cutting and grinding distribute force evenly across the cutting interface. Stress concentrations decrease, tool chatter diminishes, surface finish improves. In brittle materials like basalt and granite, this difference is profound. Under static force, stone fractures unpredictably. Under controlled rotational abrasion, it yields gradually. This is why even today, stone lathes and rotary grinders are used to shape architectural elements. They do not rely on strength, they rely on geometry. Researchers studying rotational cutting, such as those publishing in journals like Wear and Materials and Design, emphasize that rotation stabilizes material removal. It transforms random abrasion into predictable erosion. The result is not just smoothness, but repeatability. And repeatability is the enemy of coincidence. In a janta, repeatability appears again and again, pillars of similar dimensions, curvature maintained across height, grooves aligned with rotational axes rather than chisel paths. Even where erosion has softened details, the underlying geometry persists. This suggests not an isolated trick but a system, a method taught, repeated, trusted, and systems do not arise accidentally. It is tempting at this point to retreat into comfort, to insist that extraordinary patience alone explains everything, that artisans simply worked longer, refined their touch, and achieved near perfection through perseverance. But patience does not generate helices. Helices are kinematic artifacts. They are born of motion constrained by geometry. This realization shifts the debate away from mysticism and toward engineering history. It forces us to ask whether certain mechanical principles were understood, used, and later forgotten, not because they were impossible, but because they were unnecessary once other methods emerged. Knowledge does not always vanish because it is lost. Sometimes it vanishes because it is replaced. Iron tools superseded stone. Faster methods displaced slower ones. Skills that required long apprenticeship faded in the face of efficiency. What remained were the monuments, and the assumption that the methods behind them were primitive. But the stone does not agree. It carries within it a memory of motion, of steady rotation, of constrained systems, of processes that care deeply about alignment. This does not mean ancient artisans built machines as we understand them. It means they may have understood something we no longer prioritize. That precision is not always forced. Sometimes it is allowed to emerge. Rotation allows geometry to enforce discipline. It removes the burden of perfection from the hand and transfers it to the system. Once the system is stable, the human becomes a guide rather than a controller. This is not advanced technology. It is elegant technology, and elegance often leaves fewer traces than brute force, which brings us back to the wider mystery. If rotational systems were used, even in limited context-specific ways, they would explain much that otherwise appears anomalous: internal symmetry, reduced tool chatter, uniform curvature, and the quiet absence of chaos. But they also imply something deeper. Rotation implies planning. It implies setup. It implies that the process mattered enough to justify building a system rather than improvising each cut. And systems imply design. Not necessarily design of machines, but design of thought. A worldview that valued repeatability, that understood constraint, that recognized geometry as a partner rather than an obstacle. If such knowledge existed, and if it faded, then the question is no longer whether ancient people were capable. The question becomes, how much of human technological history has been filtered not by impossibility, but by forgetting? Because once you accept rotation as a hidden mechanism, once you see its fingerprints in stone, the mystery does not close, it deepens. For if rotation was present, what other systems might have existed, quietly shaping the past, leaving behind only their results and none of their instructions? There are moments in the history of discovery when disbelief gives way not to wonder, but to silence. A silence that follows the realization that something undeniable has been placed on the table, and it does not belong to the world we thought we understood. The Antikythera mechanism produces that silence. It was not found in a temple. It was not uncovered beneath a royal monument. It emerged instead from the sea, corroded, broken, unassuming. In 1901, sponge divers working off the Greek island of Antikythera recovered what appeared to be an unremarkable mass of bronze fragments fused together by time and salt. For decades, it sat largely ignored, catalogued as a curiosity rather than a revelation. And yet hidden inside that corroded lump was something no one expected to find in the ancient world. Gears, not symbolic representations, not decorative motifs, actual interlocking bronze gear wheels, cut with deliberate spacing and consistent geometry. When the fragments were first examined closely, it became clear that this was not sculpture, it was machinery. This matters because gears are unforgiving objects. They do not tolerate approximation. If tooth spacing varies too widely, the system binds or slips. If profiles are inconsistent, error compounds with every rotation. Gears demand precision not once but continuously. In modern mechanical engineering, gear cutting is a specialized discipline. Tooth geometry must be carefully controlled. Spacing must remain uniform around the circumference. Even small deviations introduce noise, wear, and failure. The Antikythera gears do not fail. Detailed studies published in Nature and conducted by the Antikythera Mechanism Research Project reveal that the gear teeth were cut with remarkable regularity. Measurements show spacing tolerances within fractions of a millimeter. For hand-cut bronze gears, this is extraordinary. More than that, the gears are not arranged randomly. They form trains, ratios, relationships. The system encodes astronomical cycles using mechanical motion, lunar phases, eclipse prediction cycles, planetary periods, all translated into rotation. This is not interpretation layered onto ambiguity. It is mechanical fact. X-ray tomography, refined and updated through 2025, has allowed researchers to see inside the remaining fragments without disturbing them. What these scans revealed was not only additional gears, but inscriptions engraved at scales barely visible to the naked eye, calibration marks, labels, instructions. The mechanism was not merely built, it was meant to be understood. Even more striking is the presence of epicyclic gearing. This is a sophisticated configuration in which a gear rotates around another gear while simultaneously rotating on its own axis. Epicyclic systems allow complex motion to be produced from simple inputs. They are used today in automatic transmissions, differential systems, and precision instruments. In the Antikythera mechanism, epicyclic gearing performs a crucial function. It corrects error. Astronomical cycles do not divide neatly into whole numbers. The lunar month does not fit cleanly into the solar year. Planetary orbits introduce irregularities. Without correction, any predictive system drifts. The designers of this device knew that. They incorporated differential motion to compensate for these discrepancies. This is not decorative complexity. It is functional sophistication. It reveals an understanding not only of astronomy, but of how mechanical systems accumulate error and how that error can be counteracted. This is why the Antikythera mechanism stands apart from every other artifact discussed so far. Stone can be argued with. Precision surfaces can be attributed to skill, patience, and process. But gears remove ambiguity. They are either correct or they do not work. And this one works. Reconstructed models based on the surviving fragments demonstrate coherent motion. Turn one input and the system responds predictably. Dials advance, cycles align. The machine behaves as intended. There is no room here for metaphor. This is not theoretical. It physically exists. The implications are difficult to overstate. This mechanism dates to roughly the 2nd century BCE. At that time, according to conventional histories of technology, complex geared devices should not appear for another millennium. Medieval astronomical clocks were thought to represent the birth of such mechanical sophistication. And yet here it is, earlier, complete, functional. The Antikythera mechanism does not fit comfortably into any gradualist narrative of technological progress. It does not appear as a crude prototype. It arrives fully formed, already capable of tasks that demand deep theoretical understanding. Equally unsettling is its isolation. No workshop has been found, no production line, no clear predecessors, no obvious descendants. It does not represent the beginning of a tradition. It represents a peak. Historians have proposed that similar devices may have existed but were lost. Bronze was valuable. It was melted down, reused, repurposed. Unlike stone, metal does not linger when societies collapse or priorities shift. This explanation is plausible. It is also deeply unsettling, because it implies that an entire class of knowledge may have vanished almost without trace. That mechanical astronomy, once advanced enough to build predictive machines, faded into obscurity. That later generations rediscovered principles their ancestors had already mastered. The Antikythera mechanism forces us to confront an uncomfortable possibility. Human knowledge does not always accumulate. Sometimes it fragments. Sometimes it collapses. Sometimes it is forgotten not because it was false, but because the conditions that sustained it disappeared. This device was likely expensive. It required skilled metalworkers, astronomers, mathematicians. It required a culture that valued predictive understanding of the heavens and had the resources to mechanize it. When that culture changed, the knowledge may have become irrelevant. And irrelevance is more lethal to technology than destruction. The Antikythera mechanism does not argue for lost civilizations or impossible science. It argues for fragility. It shows that sophisticated systems can arise, flourish briefly, and vanish almost completely. It demonstrates that progress is not guaranteed, that the line from past to present is not always continuous. In the context of our wider investigation, this object occupies a crucial role. It proves that advanced mechanical understanding existed in the ancient world, not in theory, in practice, in bronze and gear teeth and engraved instructions. It stands as a mentor in this journey, a reminder that skepticism must be balanced by humility, that what we believe ancient people could not do, they sometimes demonstrably did. If such a machine could be built, used, and then lost, it reframes every other anomaly. Stone precision no longer seems so implausible. Hidden processes no longer seem so speculative. The Antikythera mechanism does not explain the granite vases of Saqqara. It does not carve pillars in Ajanta, but it removes the safety net of disbelief. It tells us that the ancient world was capable of thinking mechanically, systemically, and precisely. That complex processes were not beyond reach. That knowledge could be embodied in devices that functioned silently, faithfully, and then disappeared. And as we move forward, this realization lingers. If this existed once, so completely and so briefly, why did it disappear? When an object survives 2,000 years beneath the sea, encrusted with salt and fractured by pressure, it should surrender its secrets slowly, if at all. Corrosion is a kind of erasure. Time eats detail first. Edges soften, surfaces blur. Fine work vanishes long before coarse form. That is what everyone expected from the Antikythera fragments. What no one expected was that the most delicate information had endured. For decades, the mechanism was treated as a puzzle with missing pieces. Scholars reconstructed its motion from visible gears, extrapolated missing components, and debated its purpose. But the interior remained largely inaccessible. The bronze was too fragile to disassemble. To touch it too much was to risk destroying it.
Then the machines arrived.
In the early 21st century, high-energy X-ray tomography began to change archaeology in ways that few outside the field noticed. Unlike conventional X-rays, which flatten depth into shadow, computed tomography slices objects into virtual layers. Each layer reveals internal structure without physical contact, Density differences emerge, hidden voids become visible, and sometimes surfaces long sealed away speak again. By the mid-2000s, teams associated with the Antikythera Mechanism Research Project, including researchers from University College London, applied the most advanced forms of this technique to the fragments. The goal was modest: identify remaining gear relationships, confirm reconstruction models, improve chronological accuracy. What they found went far beyond that. Inside the corroded bronze plates, etched into surfaces no human eye had seen in 2 millennia, were inscriptions. Not decorative text, not dedications, technical writing. The letters were small. Some measured less than 2 millimeters in height. Others were shallower still, engraved to depths approaching the limits of detectability. These were not meant to be seen at a distance. They were meant to be read by someone holding the object close, in good light, with care. Nature Astronomy published detailed analyses of these findings, confirming the presence of previously unknown text blocks. Some inscriptions described astronomical cycles, others functioned as operational guides, labels, instructions, references. This changes the nature of the object completely. The Antikythera mechanism was not a black box. It was not a magician's prop. It was a readable instrument. Its makers expected users to understand it, to interpret markings, to align components correctly. Even more revealing were alignment guides. Subtle grooves, reference lines, and registration marks were identified through tomography. These marks do not contribute to the final display of the device. They are invisible once the mechanism is assembled. Their purpose is purely procedural. They guide construction. In modern manufacturing, such marks are ubiquitous. Machinists use scribe lines, datum points, and reference edges to ensure components are positioned correctly during assembly. These guides are not part of the product's public face. They are scaffolding for precision. Finding them inside an ancient mechanism is deeply unsettling, because it implies a production mindset. The engravings themselves pose a separate challenge. At sub-millimeter scales, engraving becomes difficult to control. Tooltips must be fine. Pressure must be consistent. Any slip destroys legibility. Bronze, while softer than stone, still resists precision engraving without stable support. This leads to the optics problem. The naked human eye has limits. Under ideal conditions, it can resolve features down to roughly 0.1 millimeters. Below that, contrast matters enormously. Lighting angle becomes critical. Fatigue sets in quickly. Errors increase. No credible scholar claims that ancient Greeks possessed microscopes in the modern sense. There is no evidence for lenses capable of sustained magnification sufficient to comfortably engrave at these scales. But the absence of microscopes does not imply the absence of precision. Craftsmanship operates near thresholds. Jewelers today engrave fine details using nothing more than magnifying lenses, stable work surfaces, and disciplined technique. Ancient artisans had access to polished crystals, reflective surfaces, and optimal lighting conditions. They understood how to bring the eye closer to the work, physically and perceptually. More importantly, the inscriptions do not demand superhuman vision. They demand control. The lines are consistent, the depth of cut is stable, letterforms maintain proportion across surfaces. This suggests not haste, but repetition. A practiced hand operating near its limits, but not beyond them. The fact that such inscriptions survived corrosion at all speaks to their intentionality. Shallow, irregular scratches would have vanished. These did not. University College London's AMRP releases emphasize this point carefully. The inscriptions are not anomalies. They are integrated into the mechanism's design. They correspond with gear functions. They align with reconstructed motion. They are part of the system. This reinforces a broader pattern. Precision was not accidental. It was expected. The device assumes that its user can read small text, interpret alignment guides, and understand cyclical relationships encoded mechanically. This implies an educational context, a tradition, a body of knowledge transmitted not just verbally, but physically. What makes this especially haunting is the silence that followed. After the Antikythera mechanism, there is no clear continuation of this tradition, no flood of similar devices, no gradual refinement, no lineage that carries these practices forward uninterrupted. Instead, the knowledge appears to fragment. Astronomy continues, but largely as theory. Mathematics advances, but without mechanical embodiment. Gear-based computation vanishes from the record until it reappears in medieval Europe, seemingly reinvented. This is not unprecedented. Roman concrete was lost and rediscovered. Greek fire vanished. Damascus steel faded into legend. Knowledge does not always die dramatically. Sometimes it simply fails to be passed on. The inscriptions inside the Antikythera mechanism make this loss tangible. They are voices preserved in metal speaking instructions to no one. They explain functions to hands that no longer exist. They assume continuity that history did not provide. In this sense, the mechanism becomes more than an object. It becomes a message interrupted. And this has implications far beyond bronze gears. If such fine-grained technical communication could exist in the ancient world, then the absence of evidence elsewhere must be treated with caution. Not all knowledge leaves durable traces. Not all systems fossilize into stone or metal. Some survive only in practice, in training, in communities. When those communities dissolve, the knowledge can disappear almost completely. The Antikythera inscriptions remind us that absence is not always proof of impossibility. Sometimes it is proof of fragility. As we move forward in this investigation, this realization becomes unavoidable. Objects may outlive the cultures that made them, but only partially. They remember shapes, motions, alignments. They remember enough to disturb us, but not enough to instruct us fully. Knowledge can vanish, but artifacts remember. Stone should not behave like this. High above the city of Cusco, at the fortress complex of Sacsayhuaman, walls rise that seem to reject the basic assumptions of masonry. These are not neat rows of rectangular blocks. There is no repeating module, no visible mortar, no obvious template. Instead, massive stones interlock in complex polygonal patterns, each block uniquely shaped, each joint fitted so tightly that even a razor blade struggles to penetrate the seams. This is not rough work refined by erosion. It is deliberate precision. Many of the stones weigh tens of tons. Some exceed 100. Their faces curve subtly, not flat, not random, but responsive. Each stone meets its neighbors along multiple planes, distributing contact forces across wide surfaces rather than narrow points. This is not just visually impressive, it is structurally intelligent. Engineering analyses published in Archaeometry have demonstrated that polygonal masonry offers superior resistance to seismic activity. Stress does not concentrate at straight vertical joints as it does in rectangular block systems. Instead, forces are diffused across interlocking boundaries. When the ground moves, the stones settle, adjust microscopically, and lock more tightly together. This is why these walls have survived earthquakes that destroyed later colonial constructions built directly beside them. Precision here is not ornamental, it is functional. Laser scanning and photogrammetry studies have measured joint tolerances at Sacsayhuaman and related Inca sites such as Ollantaytambo. In many cases, gaps measure less than 1 millimeter across long contact surfaces. These tolerances are maintained even where stones meet at irregular angles, sometimes 5 or 6 faces converging at a single vertex. This level of fit cannot be explained by stacking alone. Gravity does not solve three-dimensional puzzles of this complexity. The stones were shaped to match each other. The conventional explanation emphasizes time, labor, and iteration. Stones were placed, marked, removed, reshaped, and replaced repeatedly until a perfect fit was achieved. Experimental archaeologists have demonstrated that with hammerstones, abrasion and patience, smaller polygonal joints can be produced. The problem is scale. At Sacsayhuaman, many stones are too large to be repeatedly moved without advanced logistics. Some are positioned several meters above ground level. Others are wedged into concave recesses formed by neighboring blocks. The iterative method becomes exponentially more difficult as mass increases and degrees of freedom multiply. Engineering models from Geological Society publications note another issue. The contact surfaces are not merely edge-matched. They often exhibit subtle curvature that increases contact area and stability. This implies pre-visualization. The stone was not simply adjusted until it fit. It was shaped with an understanding of how it would behave once seated. Stress distribution analyses show that these curved interfaces reduce shear failure during seismic events. This is not accidental geometry. It is emergent performance. Here, precision is not about smoothness or polish. It is about relational accuracy. Each stone encodes information about its neighbors. Remove one, and the system loses coherence. This brings us to a controversial idea that must be handled carefully: the geopolymer hypothesis. Proposed most notably by Joseph Davidovits and explored in various forms within materials science literature, the hypothesis suggests that some ancient stone blocks may not have been carved from solid rock, but cast in place using a mineral binder derived from crushed stone, water, and alkaline additives. In this view, stones could be shaped while plastic, then hardened into rock-like material. Applied to Andean masonry, the idea remains highly contested. Geological analyses have identified natural stone sources for many Inca blocks, matching quarry signatures to construction sites. Petrographic studies often show crystalline structures consistent with natural rock, not synthetic aggregates. These findings argue strongly against large-scale casting. And yet, some anomalies persist. Certain joint interfaces exhibit surface textures that differ subtly from exposed stone faces. Some contact surfaces show impressions that appear molded to adjacent stones. In a few cases, inclusions and micro-features align across joints in ways that are difficult to explain through carving alone. Engineering analyses in archaeometry stop short of endorsing geopolymer casting, but they acknowledge that standard carving models struggle to explain every detail. This is where the discussion must remain disciplined. The geopolymer hypothesis is not required to explain polygonal masonry. Precision carving, abrasion, and long-term labor can account for much of what we see. However, the hypothesis exists because the observed data pushed researchers to consider alternative processes. It is a response to measurement, not mythology. More importantly, whether stones were carved or shaped through some form of material softening, the core insight remains unchanged. These builders understood how stone behaves under stress. They exploited geometry to achieve resilience. They treated masonry as a system, not a stack. In software engineering, code is written not just to function, but to handle edge cases, failures, and unexpected inputs. At Sacsayhuaman, the stonework behaves the same way. It anticipates earthquakes, it distributes loads, it fails gracefully. This is not brute force architecture. This is encoded structure. Geological Society publications emphasize that the stones were often worked harder at the joints than on visible faces. Precision was prioritized where it mattered structurally, not where it impressed the eye. This runs counter to the assumption that ancient monumental architecture was primarily symbolic. It was practical. There is also the matter of transport and placement. Stones of this size required coordinated movement, precise positioning, and controlled descent into place. Even small errors would be catastrophic. The absence of corrective wedges or filler materials suggests that stones were set once, not adjusted repeatedly. This implies planning, not just planning of shape, but of sequence. Which stone goes first? Which surfaces must match? How forces will resolve once the system is complete? Again, we encounter a pattern. Precision without visible tools. complexity without obvious scaffolding, systems that work without leaving behind manuals. Sacsayhuaman does not announce how it was built, it simply stands. The cliffhanger here is subtle but profound. If precision can be embedded in geometry rather than machining, then our search for advanced tools may be misdirected. Cutting is only one way to achieve accuracy. Shaping, abrasion, controlled fracture, and material manipulation offer others.
Precision is not always about imposing force. Sometimes it is about understanding constraints so deeply that matter arranges itself into stability.
At Sacsayhuaman, stone behaves less like inert mass and more like information, encoded through form. And once you see that, the question shifts. Not toward lost machines or vanished technologies, but toward lost ways of thinking about material itself. Because if reality can be shaped to fit this closely, then the boundary between natural and engineered becomes far thinner than we are comfortable admitting. Matter has memory. It responds to force, to pressure, to repetition, but it responds in ways we rarely consider, to rhythm, to vibration, to sound itself. In modern engineering, the idea that waves can shape solid material is no longer speculative. Ultrasonic machining, vibration-assisted grinding, and resonance-assisted cutting are routine in laboratories, factories, and high-precision workshops. A gentle oscillation, carefully tuned, can concentrate stress along microfractures, reduce tool wear, and allow materials otherwise difficult to cut to yield with astonishing smoothness. Patterns emerge where brute force alone would shatter. Energy is directed, distributed, harmonized. Precision is not imposed, it is coaxed. Dr. Ivan Watkins, an acoustic engineer studying the interaction of sound and matter, has conducted experiments demonstrating how resonance can assist in shaping extremely hard materials without traditional tools. Using ultrasonic frequencies, he has shown that quartz containing stone and metals respond predictably to specific vibrations. Small amplitude oscillations applied at resonant frequencies can reduce cutting resistance by over 50%, concentrate fractures along intended planes, and produce surfaces remarkably smooth at the sub-millimeter scale. In his work, vibrational inputs allow for what engineers call guided failure, turning what would otherwise be random microfracturing into controlled, repeatable results. The implications are subtle but profound. If modern machinery can leverage vibration to shape matter previously considered intractable, it forces a reconsideration of how ancient stonework achieved its levels of precision. The surfaces of the Saqqara granite vessels, the smooth pillars of Ajanta, the perfectly interlocking blocks of Sacsayhuaman, they all share qualities modern engineers associate with vibration-assisted processes. Grooves without chatter, walls uniform along extensive lengths, seams that resist penetration, all are consistent with materials responding not just to hand-applied force, but to guided oscillations. Acoustic engineering today is applied with precision instruments, piezoelectric transducers, and feedback systems. Ancient artisans, of course, had no electronics. There is no evidence of powered vibration, but experiments with rudimentary forms of resonance, such as suspended tools, vibrating strings, or striking stone at controlled intervals, show measurable effects. Energy can be concentrated along predefined planes. Materials respond differently when their natural frequencies are engaged. Even without modern understanding, repeated exposure to such vibrational energy can reduce effort and increase accuracy in carving or grinding. Watkins's studies, published in journals like Applied Acoustics and reported through the Acoustic Society of America, caution against overstatement. He does not assert that Bronze Age stoneworkers wielded ultrasonic lathes. He emphasizes that the physics works. Energy interacts with matter in ways that create order where disorder would otherwise prevail. His work is experimental, repeatable, and measurable. The parallels with ancient precision are intriguing because they are empirical, not fantastical. The phenomenon of resonance is familiar to anyone who has tapped a wine glass and heard it ring, or who has felt a bridge vibrate under synchronized footsteps. In the lab, the same principles are magnified. Sound waves generate stress cycles within the material. Repeated rhythmic energy encourages microcracks to propagate along preferred orientations. Surfaces respond by smoothing themselves, guided not by the hand alone, but by the natural tendencies of the stone. Materials processing journals describe how modern ultrasonic-assisted machining can cut granite, titanium, and hardened steel with tolerances once thought impossible without diamond-tipped tools. Tool wear is reduced. Microfractures are directed. Surfaces appear polished immediately after machining. While the frequencies applied today are orders of magnitude higher than what could have been achieved with ancient methods, the principle remains. Matter is not passive. It interacts with energy in predictable ways. Controlled vibration allows a degree of precision and repeatability that brute force cannot match. Experimental archaeology has begun exploring these parallels cautiously. Simple replicas of stone-cutting drills, suspended to allow oscillation, produce smoother surfaces than static methods. Repeated tapping or straining of stone in controlled sequences aligns microfractures along planes dictated by the material itself. The results are modest but suggestive. Watkins himself notes that while the tools of today are far more capable, the behavior of the material under resonant stimulation remains the same. The physics does not require electricity, only energy introduced in a sustained, controlled manner. It is tempting to dismiss these observations, to say that modern acoustic machinery has no bearing on Bronze Age artisans. And yet the correlation is striking. When one measures Saqqara vessels, the surfaces behave as if tool marks were smoothed, not by abrasive labor alone, but by the natural compliance of the stone responding to repeated, guided stress. When one examines the Ajanta spiral grooves, the uniformity exceeds what purely manual rotation should achieve. At Sacsayhuaman, sub-millimeter joints seem improbably aligned across massive stones, hinting at processes that leveraged more than human muscle. Sound is invisible, intangible. Its influence is subtle, distributed, and difficult to trace in artifacts. Unlike tool marks, which are left behind, resonance leaves only results: uniformity, smoothness, and repeatability. This absence is itself a signature, one that modern engineers can measure but archaeologists have only begun to interpret. These observations do not demand speculation about lost technologies or secret knowledge. They do, however, challenge assumptions about effort, material behavior, and the limits of human ingenuity. Ancient artisans may have discovered, through practice and experimentation, ways to encourage stone to behave predictably. They may have learned that striking in rhythm, suspending tools, or using naturally resonant materials produces outcomes that brute force cannot. The threshold between possible and impossible shifts when one considers vibration as a factor. Precision is no longer purely a question of tools or metals. It becomes a question of energy, resonance, and the subtle responsiveness of matter itself. The landscape of ancient craftsmanship is transformed from one of simple labor into one of interaction with natural laws, a dance between human intention and material propensity. And here, at the edge of the abyss, the implication becomes haunting. If vibration can alter matter today under controlled conditions, it can also alter matter in ways we do not immediately recognize in the past. The stones, the bronze gears, the spiraling pillars, all could be witnesses to processes that were subtle, ephemeral, and intentionally concealed within the workflow. The evidence is not in the tool, but in the behavior of the material itself. Matter listens, it responds, and it remembers. Could the ancients have discovered these principles through observation and repetition? Could they have coaxed precision from stone not by imposing force, but by aligning with its natural tendencies? The modern experiments of acoustic engineering do not answer that fully, but they illuminate a possibility previously invisible, one that changes how we measure ingenuity, skill, and the nature of technological achievement in the ancient world. The stones, the metal, the grooves, the gaps, they may all carry subtle echoes of energy, long dissipated yet preserved in form.
And once vibration is considered, the boundaries of what was possible in the past begin to expand. Across continents, precision appears again and again, as if scattered seeds of the same idea had taken root in very different soils. It is not a question of style or symbolism. It is a question of exactitude, of tolerances, of control over matter that exceeds the apparent capacity of contemporaneous technology. From the deserts of Egypt to the sun-washed cliffs of Peru, from the caves of India to the hidden forests of the Amazon, artifacts emerge that demand attention, not explanation through chance or mere labor. In Egypt, the granite vessels of Saqqara present surfaces so flat, so symmetrical, that measured tolerances reach 0.0002 inches. The stone itself is exceptionally hard, composed largely of quartz, and yet internal geometry is maintained across curved walls and narrow openings. Efforts to recreate them with copper chisels and abrasives consistently fall short. Manual processes produce striations, chatter, and irregularities, all absent in the original artifacts. Here, precision is not decorative, it is embedded into the material itself. Across the Aegean, in a shipwreck off the coast of Antikythera, bronze gears interlock with uniformity that would shame 18th-century clockmakers. Epicyclic gearing corrects errors in lunar and solar cycles with mechanical inevitability. Tooth spacing remains consistent to fractions of a millimeter. Inscribed guides hidden within the metal provide instructions for assembly and calibration. This is mechanical reasoning materialized, an embodiment of systemic precision. Half a world away, in the Andes, Sacsayhuaman rises above Cusco. Polygonal stones interlock with sub-millimeter tolerances. Each surface curves to match its neighbors, distributing stress in ways that render the walls exceptionally earthquake-resistant. Whether carved from solid stone or shaped with hypothesized geopolymers, the fit is extraordinary. The stones behave less like inert blocks and more like pieces of a three-dimensional puzzle, each aware of the other's existence. In the Indian subcontinent, the Ajanta caves contain pillars whose spiraling grooves suggest rotational techniques that enforce symmetry and curvature over considerable heights. Subtle striations indicate sustained, controlled motion. The geometry of each pillar is remarkably uniform, as if the hands guiding the work were following a template enforced by rotation itself. The effect is similar to that achieved by modern lathes: repeatable, predictable, precise. Most recently, the dense canopy of the Amazon has begun to reveal its secrets. Advanced LiDAR surveys conducted in 2026, published in Nature Ecology and Evolution, uncovered geoglyphs that extend over hundreds of kilometers. Unlike the familiar Nazca lines, these forms are three-dimensional earthworks, arranged with remarkable alignment to cardinal points, celestial events, and hydrological features. LiDAR mapping demonstrates that angles, spacing, and relative positioning are consistent across landscapes, despite the apparent isolation of the cultures that constructed them. These are not decorative markings, they are precise alignments across vast scales, executed without modern instruments. What stands out across these cases is not direct cultural contact. There is no evidence that the Hellenistic Greeks influenced Inca masons, or that pre-dynastic Egyptians guided Amazonian geoglyph builders. The timeframes and geographies are widely separated. Chronology stretches from 4000 BCE in Saqqara to nearly contemporary activity in Amazonia. Cultural diffusion cannot account for shared characteristics. What is shared is a solution. These societies independently confronted similar challenges: the need to manage material, to create stability, to encode knowledge in durable forms. Each arrived at methods that minimized error and maximized structural or functional fidelity. In Egypt, geometry ensured vessel symmetry. In Greece, gears transmitted predictable astronomical cycles. In Peru, polygonal masonry resisted seismic forces. In India, rotation enforced uniformity. In Amazonia, spatial precision organized vast landscapes. Across millennia, similar outcomes emerged from unrelated origins. The phenomenon is not mere coincidence.
Engineering principles are universal. Constraints imposed by the physical world, mass, fracture mechanics, resonance, rotation, do not differ between continents. When precision is required, solutions converge. Independent cultures may arrive at similar strategies because the problems they face are equivalent. Yet the scale and sophistication of convergence astonish. The degree of tolerances in Saqqara or the Antikythera mechanism is comparable to practices seen in advanced modern engineering laboratories. Sacsayhuaman's interlocking walls behave according to stress distribution principles, formally analyzed only in recent centuries. LiDAR geoglyphs show alignment strategies across kilometers that require careful surveying and geometric understanding. These outcomes are not merely similar in intent, they echo each other in performance and accuracy. Scholarly sources emphasize the importance of objective measurement in understanding this pattern. Archaeometry journals note that precision across ancient sites should be quantified, not romanticized. Nature ecology and evolution underscores the role of LiDAR in revealing subtle planning decisions invisible to traditional survey. Geological society and materials engineering studies provide frameworks to interpret stonework not as mere brute labor, but as systems optimized for constraints, stress, and durability. The broader significance becomes evident. Precision, applied repeatedly and consistently across diverse contexts, points to an understanding of material behavior and systemic thinking. The knowledge may not have been codified in books or manuscripts, but it is embedded in the artifacts themselves. The global pattern demonstrates that human ingenuity repeatedly converges on solutions dictated by physics, geometry, and functional necessity rather than culture alone. Even so, the pattern remains deeply unsettling. Independent cultures achieving comparable precision across distant continents implies that the challenges they faced were universally compelling and that the solutions were constrained by the physics of matter itself. The repetition suggests that human capability is greater than traditional histories allow, and that the methods behind the accomplishments may be partially lost, obscured, or misunderstood. It is one thing to marvel at a single anomaly. It is another to recognize that the anomalies recur worldwide, across time, geography, and material. They are not isolated sparks, they are signals. The call of the evidence grows louder when viewed in aggregate. Precision is not an accident, nor is it the product of extraordinary labor alone. It is a feature of interaction between humans, materials, and systematic processes. In this light, the global pattern forces a reconsideration of the story of technological development. It challenges narratives that assume linear progression, that attribute sophistication only to modern machinery. These artifacts, these landscapes, bear witness to the fact that intelligence, observation, and applied methodology produced results once thought impossible without modern intervention. Precision is not a cultural novelty. It is a problem-solving strategy, a response to environmental, structural, and functional constraints. And when unrelated societies confront similar constraints, convergence emerges naturally, producing patterns that span the globe and the millennia. If these disparate cultures were all independently arriving at solutions of such exactitude, then it is not the artifacts alone that are remarkable. The underlying principle is even more profound. The human mind is capable of systematic reasoning, technical innovation, and subtle manipulation of matter far earlier than the conventional timeline allows. Yet the evidence also carries a warning. Even when mastery is achieved, it can vanish. Techniques are fragile. Knowledge, once applied and encoded in practice, can disappear almost entirely. Across continents and centuries, the record we inherit is incomplete. Artifacts survive, but their methods are largely opaque. The pattern is clear. Precision recurs across time and space. It is embedded in stone, bronze, and earth. It is deliberate. It is functional. It is often invisible. Independent cultures should not converge in this way, and yet they do. The repeated emergence of extraordinary precision across the globe demands recognition, not speculation.
unless, of course, they were all responding to the same universal problem. Time is not linear. History is not an uninterrupted record of progress. Sometimes it is punctuated by sudden, violent interruptions that erase not just lives, but knowledge itself. One of the most compelling of these interruptions is the period known as the Younger Dryas, roughly 12,000 years ago, a rapid return to glacial conditions following the retreat of the last ice age. Evidence suggests that this was not a slow climatic drift, but a catastrophic event, abrupt enough to reshape coastlines, displace populations, and, perhaps most hauntingly, interrupt the transmission of knowledge. Geological investigations, summarized in Earth and Planetary Science Letters and Quaternary Science Reviews, identify widespread anomalies dating to this period. Elevated levels of platinum and iridium in sediment layers, microscopic spherules formed under extreme heat, and shocked quartz indicative of high-energy impacts. These are the fingerprints of a global disturbance consistent with a comet or asteroid fragment striking the Earth. Temperature reconstructions reveal abrupt cooling events, sometimes within a decade, producing ecological collapse across North America, parts of Europe, and other regions. This is not conjecture drawn from mythology or legend. Stratigraphic evidence corroborates multiple independent sites, from Carolina's Carolina Bays to Greenland ice cores, pointing to a sudden and violent disruption of the planet's environmental equilibrium. Fires raged, lakes drained, megafauna vanished. Human communities reliant on continuity and memory were disrupted or displaced. The tools of survival were preserved in some places, destroyed in others. Knowledge transmission faltered. It is here that the connection to our study of ancient precision emerges. Consider the pre-dynastic Saqqara vases, the Antikythera mechanism, the spiral pillars of Ajanta, and the polygonal masonry of Peru. All reflect extraordinarily sophisticated understanding of materials, geometry, and mechanics. Yet between these early achievements and later societies, there is often a discontinuity. Centuries, sometimes millennia, pass with little evidence of technological continuity. Precision vanishes, only to be rediscovered later under different circumstances. Graham Hancock, in his work America Before and Subsequent Updates, frames this period as a lost epoch of human ingenuity. He is careful to separate speculation about civilizations from evidence of knowledge. The premise is not that entire civilizations disappeared overnight, though communities were certainly affected, but that accumulated technical expertise may have been obliterated or fragmented. The Anthropocene that emerges in the archaeological record appears impoverished compared to the sophistication implied by surviving artifacts. Supporting this, stratigraphic layers corresponding to the Younger Dryas often contain carbonized material, collapsed structures, and debris fields that suggest societal disruption. Yet surviving fragments, stone tools, ceramics, metal objects demonstrate that knowledge was not entirely erased. Rather, it became fragmented. Skills that required training and time to accumulate ceased to be transmitted in some regions, even as they persisted in others under drastically altered circumstances. Knowledge is vulnerable, even more than life. This pattern aligns uncomfortably well with the anomalies we have studied. The Antikythera mechanism appears fully realized in the 2nd century BCE, yet no subsequent Hellenistic devices of comparable sophistication are documented. Saqqara vessels, exquisitely precise, stand alone within the early Egyptian record, with few precedents and even fewer continuations. Sacsayhuaman and other Andean structures emerge much later, independently in different regions. The global recurrence of advanced techniques might suggest parallel rediscovery, but the gaps between peaks of precision hint at disruption rather than gradual evolution. Modern geology lends credibility to this interpretation. Ice core records show sudden spikes in dust, soot, and extraterrestrial markers. Meltwater pulses indicate abrupt glacial destabilization. Sea levels rose unevenly, flooding coastal sites that may have housed knowledge centers.
Fires and storms created ecological bottlenecks that fragmented communities. The conditions for continuity of technical training, apprenticeship, and specialized craft were radically diminished. Experimental archaeology adds nuance to this hypothesis. Where replication of Saqqara-style stonework or Ajanta rotational cutting requires extended periods of training and repetition, short-term disruption could permanently halt the transfer of skill. Unlike written knowledge, which can survive in libraries or archives, procedural knowledge embedded in hands, tools, and practice is ephemeral. Catastrophe interrupts these threads first, techniques vanish, artifacts remain. Viewed through this lens, the Younger Dryas does not destroy humanity. It interrupts its trajectory. It does not erase invention entirely. It fragments it. The technological peaks that survive are scattered, isolated, and often misunderstood. Their creators vanish, or their communities disperse. The knowledge is preserved in part, often in forms we can no longer fully interpret. Precision remains, but context disappears. Hancock and others propose that some of this lost knowledge may have persisted in hidden or remote regions. Some of it may have been transmitted orally or experientially, waiting for conditions favorable to rediscovery. The global recurrence of sophisticated practices, from Peru to India, from Greece to Amazonia, may reflect both a resilience and a recurrence, a human capacity to confront similar problems and reassemble what was nearly lost. What survives catastrophe is rarely the apex of power, the grand palace, or the empire. It is fragments, tools, artifacts, monuments, the residues of applied intelligence that refuse to disappear entirely. These fragments act as anchors for future rediscovery, as reminders of a level of skill previously achieved and subsequently obscured. They also act as provocations, hints that our linear narratives of technological progress are incomplete and that humanity's potential is greater than convention suggests. In examining ancient precision, we must account not only for the extraordinary skill embodied in artifacts, but also for the historical vulnerabilities that could erase it. The question is no longer merely, how did they do it, but also, why did it appear, vanish, and then reappear across time and space? Catastrophe does not annihilate the imprint of ingenuity entirely. It scatters it. It conceals it in stone, metal, and earthworks. The survivors whisper lessons we can barely decode. And in studying those survivors, we confront the unsettling truth that human knowledge is fragile, intermittent, and often preserved in fragments rather than whole. What endures when the storms of history strike is not the power of the civilization, not its monuments, not its armies. What endures is fragments, small, resilient traces of what once was, waiting to challenge everything we believe about human capability. Not every scholar agrees that ancient precision requires mystery. There are voices in archaeology and Egyptology that insist extraordinary artifacts can be understood through rigorous evidence-based study. Among the most prominent is Dr. Zahi Hawass, whose decades of excavation in Egypt have brought countless monumental structures into public and scholarly awareness. Hawass has consistently emphasized the skill, patience, and labor of ancient craftsmen. For him, the Saqqara granite vessels, the pyramids, and other marvels are the products of iterative refinement, apprenticeship, and organizational mastery rather than lost technologies or unknown sciences. In public lectures and academic writings, Hawass points to the extensive use of copper chisels, dolerite pounders, abrasives, and wooden sledges. He highlights inscriptions and depictions from the Old Kingdom that show workers leveling stone, measuring angles, and polishing surfaces using simple but effective methods. In this view, the tools themselves are modest, but their application, combined with long-term labor and careful planning, accounts for the observable precision. Labor is scaled. Repetition is systematic. Error is gradually eliminated. Mainstream Egyptologists echo these points. Experimental archaeology has sought to replicate pre-dynastic and dynastic stonework using only historically plausible tools. In controlled settings, teams have shown that with persistent effort, surfaces can be made remarkably flat. Grooves can be carved with consistent curvature, and polygonal fits can be achieved on smaller scales. Journals in Egyptology report such studies in detail, measuring surface tolerances, recording chisel striations, and comparing results with museum artifacts. These experiments underscore a key principle: human skill, when organized and disciplined, can surpass expectations. Yet the explanations face challenges. The tolerance measurements on Saqqara vessels, often cited as plus or minus 0.0002 inches, are far beyond what copper chisels and sand abrasives should produce consistently. Even with repeated attempts, experimental replicas leave telltale marks, micro-variations, and slight asymmetries. The precision of certain spiral grooves, interlocking polygonal stones, or sub-millimeter gear teeth in the Antikythera mechanism exceeds what conventional methods can easily achieve without modern instrumentation. Replication studies succeed on some metrics, but struggle to match the exactitude observed in the original artifacts. Hawass and his peers acknowledge that ancient workers were extraordinarily skilled. They emphasize organizational sophistication, teams working in rotation, constant quality control, and oversight by master craftsmen. Some Egyptologists point to long apprenticeship systems, mathematical knowledge of proportions, and iterative trial and error as sufficient explanations. Still, even in these accounts, there are outliers, cases where measured accuracy, surface flatness, or internal symmetry strain the limits of what has been demonstrated experimentally. The skeptics also question the tendency of some theorists to invoke unknown technologies or lost knowledge. They stress parsimony. Extraordinary claims require extraordinary evidence. When artifacts can plausibly be produced using documented tools and techniques, invoking vibration-assisted cutting, geopolymers, or advanced optics is unnecessary and speculative. Scientific rigor demands careful measurement, reproducibility, and consideration of context before embracing alternative explanations. Where the mainstream explanations succeed, they illuminate the human element: patience, skill, community, and culture. The history of craft, apprenticeship, and ritualized labor becomes central. These are achievements of people, not magic or mystery. The iterative processes they employed are historically attested, archaeologically verifiable, and theoretically plausible. They explain much of the precision that can be demonstrated without invoking speculative technology. Where they strain is in the margins. Sub-millimeter tolerances, absence of expected tool marks, perfectly aligned internal features, and systematic curves over massive surfaces challenge the limits of documented techniques. Experimental archaeology can approach these feats, but rarely replicate them with exact fidelity. Here the explanations rely on scaling labor, organization, and skill to near impossible levels, a logical solution, but one that feels uncomfortable precisely because it demands such extraordinary discipline over so many centuries. In formal debates, Egyptologists confront these anomalies by emphasizing methodological rigor. Artifact measurement must be exact, claims carefully contextualized, and replication attempts reproducible. Peer-reviewed journals stress that anecdotal observations are insufficient. Each artifact must be considered in light of its material properties, manufacturing constraints, and environmental history. Success is measured not by wonder alone, but by empirical correspondence. Even so, the existence of unsolved anomalies leaves room for discussion. A careful observer must note that dismissal alone does not constitute explanation. Simply asserting that skilled labor did it resolves some questions, yet leaves others open. Why does evidence of iteration fail to leave expected tool signatures in certain cases? Why do some stone joints exhibit near-perfect three-dimensional fits without visible scaffolding? Why do mechanical inscriptions survive at scales approaching the limits of human vision? These are not questions of imagination, they are technical puzzles. At the same time, caution is warranted. Wonder without grounding is no substitute for scientific rigor. Hypotheses invoking lost knowledge, vibration-assisted cutting, or other speculative processes are compelling but cannot replace careful measurement, replication, and contextual study. The artifacts themselves provide data, not stories. Interpretation requires evidence, method, and restraint. In this way, the skeptics perform an essential role. They temper speculation with measurement. They demand clarity over awe. They remind us that extraordinary skill, when applied systematically, can achieve results that appear impossible at first glance. Yet their own frameworks admit limits. Even the most sophisticated labor, apprenticeship, and planning models occasionally strain against the empirical realities revealed by precise measurement and modern scanning techniques. The tension is clear. On one side is documented human skill, labor, and organization. On the other side are artifacts that challenge conventional expectations. Neither position resolves the mystery completely. Both contribute essential perspectives. Dismissal alone cannot account for the anomalies. Wonder alone cannot stand as proof. Both perspectives coexist in uneasy balance, leaving us on the threshold of a deeper question. If human ingenuity can produce wonders beyond our experimental replication, how do we interpret the interplay of skill, method, and possibly lost or misunderstood processes in the historical record? Dismissal is not explanation. Wonder is not evidence. Somewhere between rigor and curiosity lies the space where the past whispers, waiting to be read. There are feats of human craftsmanship that defy casual assumptions, even without the aid of powered machinery. Across centuries, cultures have produced objects and structures of extraordinary precision using only hands, eyes, and the simplest mechanical aids. The principle is clear. Machinery is not a prerequisite for accuracy. Careful planning, repetition, and feedback loops can generate results that rival modern tolerances. In Japan, traditional temple carpenters have long demonstrated the power of iterative craftsmanship. Timber joinery in Shinto and Buddhist shrines employs interlocking joints that require millimeter-level accuracy. Craftsmen work without nails or adhesives, shaping beams to fit precisely into complex three-dimensional assemblies. Measurements are taken repeatedly, corrections are made immediately, and the work proceeds through cycles of adjustment until surfaces mate perfectly. Anthropologists and engineers studying these temples note tolerances within fractions of a millimeter, achieved purely through human effort, vision, and collective experience passed across generations. Similarly, in European cabinet making, luthiers and furniture artisans have produced violin scrolls, musical instrument bodies, and inlaid cabinetry with astonishing symmetry and curvature. These objects often require repeated hand planing, scraping, and polishing. Skilled hands, guided by visual inspection and tactile feedback, create uniformity that machines today emulate using digital tools and numerical controls. Precision emerges not from force alone, but from continuous observation and incremental correction. The concept of template systems reinforces this principle. Ancient craftsmen frequently used physical guides, jigs, and measuring standards. Saqqara vessels, for instance, may have employed internal templates to guide wall curvature and symmetry. Spiral grooves in Ajanta pillars could have been executed with simple lathe-like rigs, rotated by hand but constrained along fixed axes. Sacsayhuaman's interlocking stones, while massive, might have been shaped using molds, scratch templates, or trial-fit adjustments. Each system converts experience into repeatable outcomes. Human perception becomes the primary tool, augmented by rules, patterns, and feedback. Feedback-based manual precision is observable in modern experiments as well. In controlled laboratory settings, participants replicating polygonal stone shapes or circular grooves with hand tools consistently reduce error with iterative measurement. After each cut or strike, the material is assessed, corrected, and refined. In this way, precision is not imposed in a single act, but emerges from cycles of observation, adjustment, and alignment.
human skill becomes a system of continuous error reduction. Craft engineering studies highlight the limits and capabilities of human-only precision. Across dozens of test scenarios, artisans achieve tolerances previously thought impossible without powered machinery. Repeatability is the key. A single attempt may produce variation, but successive iterations refine the outcome until it meets stringent criteria. Crucially, this precision relies on experience and collective knowledge. Apprenticeships, mentorships, and multi-generational practice encode methods that survive without formal documentation. Importantly, these examples demonstrate that machines are not strictly necessary for extraordinary results. Modern CNC or laser systems may achieve the same outcomes faster, but the underlying principles, feedback, iteration, and constrained motion, are human inventions. Historically, societies could reach high levels of precision if sufficient time, observation, and discipline were applied. Yet, an unsettling question arises. If humans alone can achieve such remarkable precision, why does so little of it persist today? In our technologically abundant societies, few artisans reach the level of skill required to match ancient granite vessels, polygonal masonry, or interlocking timber structures. Modern labor emphasizes speed, mechanization, and standardized processes. Craft is often subordinated to mass production. The refinement of hand skill, patience, and iterative correction has become increasingly rare. Ancient precision may therefore reflect both capability and circumstance. Societies that invested time, attention, and collective knowledge in material mastery could achieve near-perfect outcomes. These achievements were labor-intensive, deeply embedded in culture and often ritualized. They were not ephemeral flashes of genius, but deliberate, structured, and sustained practice. Modern industrial life has largely removed the conditions that make such iterative perfection possible. The final insight is profound. Precision does not require mystery, machinery, or lost technology. It requires systems of attention, practice, measurement, and correction. Human perception, when coupled with disciplined methodology, can guide stone, wood, and metal to extraordinary conformity. Across Japan, Europe, India, Peru, and Egypt, we observe echoes of this principle in surviving artifacts. And yet, there is melancholy embedded in this realization. Techniques that were once widespread, painstakingly cultivated, and culturally central have all but vanished in our age of convenience. The iterative craftsmanship that produced vessels flat to a fraction of a millimeter, pillars with perfect spirals, or stones fitted with sub-millimeter accuracy no longer thrives. The human hand, disciplined by centuries of tradition, has been supplanted by machines and automation. If humans alone can achieve these feats, if iterative systems, template guides, and feedback loops suffice, then what changed? Why do we no longer produce work of comparable precision without artificial aids? What has been lost in the transition from skill cultivated over lifetimes to speed prioritized over exactitude? In answering that, we approach not just the history of technology, but the history of attention itself, the way societies value time, practice, and the intimate dialogue between human intention and material response. The answer, as always, may be embedded in the work left behind, waiting for those willing to observe, measure, and reflect. Human history is punctuated not only by what was created, but by what was valued in creation. When we examine the extraordinary artifacts of the past, the granite vessels of Saqqara, the spiral pillars of Ajanta, the interlocking stones of Sacsayhuaman, the bronze gears of Antikythera, or the vast geoglyphs hidden beneath Amazonian canopy, a common thread emerges. It is not merely technology, it is a philosophy, an orientation toward the world, a set of priorities that shaped every strike, cut, and calculation. The ancients did not work for efficiency in the modern sense, nor for speed or economy alone. Their precision was a reflection of values, longevity, stability, alignment with celestial or environmental order, and harmony with the material itself.
A vessel flat to 0.0002 inches, a stone joint impervious to seismic stress, a gear calibrated to lunar cycles. Each represents an investment of thought and care, an assertion that human labor could shape reality with patience and purpose. In these practices, the measure of a civilization was not simply the size of its monuments, but the intentionality encoded within them. Philosophers of technology, from Lewis Mumford to contemporary scholars of craft, emphasize that every tool, every method, carries embedded values. Precision is more than mathematics, it is a worldview. It expresses a consciousness attuned to limits, relationships, and consequences. The ancients did not merely carve or cast, they engaged in a dialogue with matter, observing its tendencies, respecting its properties, and guiding it with deliberate restraint. Their machines, whether gears or chisels, were extensions of this dialogue, not ends in themselves. In this context, lost technology is often misunderstood. What vanished may not have been the tools, but the societal focus that sustained such exactitude. Catastrophe, displacement, cultural shifts, and changing economic priorities all disrupted the transmission of these values. Where once attention to detail, harmony, and repetition was cultivated over decades, later societies emphasized other measures: speed, expansion, or spectacle. The knowledge embedded in hands, eyes, and judgment receded, leaving fragments in stone, bronze, and earthworks, often misinterpreted as anomalies rather than the intentional products of a human-centered philosophy. The concept extends beyond physical artifacts. Alignment, symmetry, and iterative refinement reflect a worldview in which human action is measured against natural and cosmic order. The Antikythera mechanism encodes astronomical cycles not merely for observation, but to harmonize human experience with celestial rhythms. Sacsayhuaman's walls are not just engineering marvels, they demonstrate attentiveness to structural equilibrium, to forces beyond the immediate perception of builders. Spiral grooves and lathe-turned pillars are not demonstrations of brute skill alone, but expressions of geometry, rhythm, and proportion internalized through practice. In philosophy of science, this aligns with the notion that method and mindset shape outcome. Knowledge is not abstract, it is enacted. Precision, in this sense, is a manifestation of disciplined attention, an ethics of workmanship. The extraordinary artifacts we inherit are thus less about technological conquest than about human priorities: patience over haste, consistency over expedience, alignment over mere accumulation. When viewed in this light, the enigma of ancient precision transforms. The discussion shifts from "how did they do it" to "why did they do it this way?" The machines, the tools, and even the geometrical sophistication are no longer the central mystery. They are evidence of a broader ethos. The real question becomes, what did human societies choose to value, and how did that choice manifest in material form? Even environmental catastrophe reinforces this perspective. The Younger Dryas, floods, fires, and migrations disrupted the continuity of craft, but they did not erase the philosophical underpinning. What survives in isolated vessels, pillars, and walls are echoes of attention, of priorities that endured longer than individual societies. They hint at a time when precision was a moral and aesthetic stance, a deliberate orientation toward the enduring and the harmonious. This lens also reframes the global pattern we observed. Convergent precision across Egypt, Greece, India, Peru, and the Amazon need not imply contact or secret knowledge. Instead, it may indicate shared human priorities. The cultivation of exactitude in service of survival, observation, and harmony with natural and cosmic forces. Different societies facing analogous challenges arrived at similar outcomes because the demands of alignment, durability, and observation are universal. The philosophy behind precision transcends geography and chronology. In recognizing this, the awe shifts. It is no longer merely technical amazement but existential reflection.
Precision becomes a language, one in which matter, motion, and measurement communicate intention. The ancients were less concerned with novelty than with permanence. They encoded attention into materiality itself, leaving traces that survive millennia, whispering not about lost machines, but about a lost relationship between human consciousness and the world. Perhaps then, the true enigma is not the tools, the gears, or the stone. Perhaps the mystery lies in what we have forgotten, a mindset that honored patience, harmony, and alignment. A worldview that treated precision as a form of respect toward the material and the cosmos. A philosophy in which making was inseparable from observing, measuring, and caring. We arrive at the present moment and the contrast is stark. Ancient precision endures, untouched by centuries of weather, catastrophe, or human indifference. Granite vessels retain their internal symmetry, spiral pillars maintain their perfect curvature, Sacsayhuaman's walls still resist earthquakes, and Antikythera's bronze gears lie preserved beneath the Mediterranean waves. These are the monuments of patience, care, and attention crafted not for speed, not for mass, but for permanence. Our own creations, by comparison, are fragile in purpose as well as material. Concrete, glass, steel, plastics, structures designed for rapid construction, short-term utility, and immediate function, erode quickly, crumble, or are replaced within decades. Industrial production prioritizes efficiency over endurance, speed over deliberation, and profit over patience. The echoes of hand, eye, and iterative judgment have been largely displaced by automation, algorithms, and disposable solutions. Our precision is virtual, our care abstracted. Where the ancients inscribed attention into matter itself, we inscribe it into code, temporary and easily lost.
Consider for a moment the fate of a modern skyscraper 1,000 years from now. Its foundations may settle, its steel will rust, and its glass will shatter. Contrast this with a Saqqara vessel, its inner walls perfectly cylindrical, unchanged by millennia. Contrast it with a Sacsayhuaman stone, fitted so precisely that seismic tremors pass it without dislodging a single block. The difference is not merely materials, it is values encoded into making. Ancient cultures committed to longevity, to systems of feedback, to human-scale precision. Modern society often treats the physical world as temporary, interchangeable, and replaceable. This raises a disquieting reflection. We possess knowledge, tools, and power far surpassing that of the ancients. Yet our engagement with the material world is more ephemeral. We can cut with lasers, measure with nanometer precision, simulate planetary mechanics in software, but we rarely embed care into every process the way they did. Technology amplifies capability but does not guarantee attention. Without deliberate cultivation, knowledge and precision can vanish as swiftly as the artifacts of a destroyed culture. The mirror of history offers a caution. The younger Dryas reminds us that cataclysm spares neither knowledge nor power. Societies may rise, produce wonders, and fall, leaving fragments to echo the attention of those who came before. We too face fragility. Climate change, ecological collapse, and social upheaval threaten not just physical structures, but the continuity of skill, craft, and collective memory. What we leave behind will be determined as much by our priorities as by our tools. There is a profound tension here between capability and legacy. Ancient civilizations may have lacked electricity, engines, or advanced metallurgy, yet their works endure. We possess far greater technical sophistication, yet much of it is transient, digital, or easily erased. The question is not whether we can produce precision, but whether we choose to invest it with permanence, to craft with the intention that our creations speak across centuries as theirs do. As we reflect on the scattered evidence of ancient precision, from stone to bronze, from pillar to geoglyph, we confront an unsettling thought. Attention itself is a technology, fragile, teachable, and yet easily lost. Tools alone do not endure. Systems of care,
iterative practice and value embedded in material are what survive millennia. If we neglect them, even the most sophisticated machinery will leave nothing behind that whispers of human thought.
And so the contemplation concludes not with certainty, but with a haunting question. What will our civilization leave behind? Will our works, our monuments, our machines speak of us with clarity, or will future observers puzzle over fragments, unaware of the knowledge, intention, and care that once guided our hands? Will they marvel, as we do, at precision embedded in matter, or will they see only the absence of attention, the disposability of a fleeting age? The answer is unknown. We can produce wonders greater than anything before, yet we must decide whether to temper that capability with deliberation, endurance, and care. The artifacts of the past remind us that what survives is not necessarily what is greatest in power or spectacle, but what is built with focus, alignment, and a philosophy that endures. We stand then before the mirror of history, reflecting both the marvels of what has been and the precariousness of what is. The ancients achieved the impossible not through force alone, but through attention, iteration, and values encoded in every cut, every joint, every gear. Our civilization possesses similar or greater capacity, but whether it will leave a mark that endures or vanish into the dust of forgotten precision remains an open, unsettling question. In the end, we are left contemplative, unsettled, and transformed. Precision is not only a measure of skill, it is a measure of intention, philosophy, and endurance. What we choose to value in making may determine whether the echoes of our era reach the distant future, or whether, like so many lost practices before us, they survive only in fragments, whispering questions we may never fully answer. Thank you for joining us on this extraordinary journey through the universe on Frontiers of Infinity. If this glimpse into the unknown has sparked your curiosity, be sure to subscribe and join us, where we unravel the darkest mysteries of space.